Okay, so got my little experiment here. Just because it was going to be hard for me to try and encode everything I'm trying to do here. This is basically just a ping pong ball that is it's symmetrical on 3/4 of it, but opposite the red thumbtacks there, as you can see. I've got to map the membrane of this thing just so that I can kind of transfer it into a circle. If you look at it, there's an asymmetry that's sort of inherent between a sphere and a circle that that a lot of people don't notice. And it's because these yellow thumbtacks here can be in two different states. In that the middle of this last quarter here, opposite 180 degrees to 0 degrees, sort of encodes some number theory in there. If you look at this, these green thumbtacks here, it sort of represents any 5 out of 6 relationship that is contained by a 4-way symmetry. So it's like 1/4 divided by 2 divided by 5, kind of all at the same time. And I need to be able to do this because with open point problems, it can be either one of those yellow points, and they tend to drift. And that's sort of represented in geometry because there's a difference between 2-dimensional and 3-dimensional geometry, and it's right here in a cone. The reason why a 2-dimensional cone is not the same as a 3-dimensional cone is because of this dimension here, this membrane, this ability for the cone to sort of flip around and flex. So if you look, this was all made out of one piece of paper, right? So we've got a membrane here that sort of contains any error along the arc of the cup, but it encodes it twice, half on one side and half on the other, right? So it turns out that this vertex here is not the center of a circle that is used to map this, and that's sort of where we get pi from. 6 of these will encompass the arc of a circle, but you need 12 of them, 12 radii, I guess, just to tell what the difference is between the cone and the circle that it was cut out of. If you look at it this way, I sort of traced it out. This is what a piece of, like the one slice of paper that is a Dixie cup actually looks like. And this is, you'll notice that this isn't the center of anything. So you can't use the same radius to draw a cone with one vertex as you use to draw the circle that contains it. So it's kind of a funny relationship between the radius and the diameter, and that a cone, neither the radius nor half the diameter describe the cone that the circle came from, which is sort of lost in a lot of mathematics, really, because if you're trying to formulate an equation and you're trying to generate some sort of equality between one side of an equation and another, you've got 3 variables. You've got, right off the bat, you've got a radius of one size. You've got a diameter that is not linked as a root cause to the radius. And then you've got an origin, a 0 point, that is essentially doubled and quartered at the same time. And it represents 1/6 of the circle. So it's sort of tough to try and design a system that incorporates all of these things. So what I came up with was a membrane. If you look at this, this little ball here, it's just a little styrofoam ball. 1/2 of it fits nicely inside this little bell-shaped toy. And on a points-based system, I can just consider 2 points on either side of this as being equivalent to this rim on the ball, right? So essentially what it does is it takes a sphere and it gives it a bias or a direction. Same as a dipole, a magnet. So this here would be convertible in terms of equations and things like this to a dipole magnet. 3/4 of a uniformity or however you wanted. Essentially, it gives this axis here some depth where it's directly proportional to the sphere of which it's a part, right? Which doesn't happen much with the cone. So if you look at the cone here, this would be sort of the encoding of the way that it would sit. The vertice of the cone would be the center of this. And then within this portion of the arc, this can tilt either way, but it's contained by this differential here, by this tangent line. So it's kind of nice because since I squished this just to fit into my little bell-shaped container, this is almost like a mold for a cone and a sphere at the same time. And my experiment today is, because you see it's notched here at particular points, I've got 4 circles going on at once. If I roll this on this piece of paper, I've got one arc of a circle right here, this large part, which is the equivalent of this. It's just larger so that it can contain this lip, right? Now I can roll this and map the circumference of it. If I take that angle out of it, that's actually just equal to a portion, a 1/8 portion of a 30, 60, 90 triangle. So what I can do is I can do something like roll this over a barcode, which I have here, and essentially map the barcode to being contained. See how the 6 and 6 are on the barcode? The 6 and 6 would be just these 2 pins right here. Sorry about my fingernails, I got ink under those. So in a P versus NP problem, this would be one point, this would be the other point, and the containment, these other variables here, would be limited not only to one portion of this arc, right, but also to a portion of a quarter of the arc, with the yellow points containing the 6s, the blue points containing the entire barcode, and that would make it a fractal of 1/7 of the arc around the sphere. Now, as long as I stay bounded by a particular equatorial perimeter, I guess, which is exactly what the point of this is, I should be able to map this membrane that will be self-similar with the same relationship at 90 degrees. So essentially, I've got 1/4 of a sphere with an equatorial plane that I can convert into a semicircle with a membrane, which is exactly what I've done here. So the way to map that is not only to map the sphere itself and the membrane, both the interior and exterior, because we know that that's going to be a fractal of itself. But I can get a second fractal using the cone as sort of a method of memory or transposition of this relationship, because it's the only conic section where this vertice doesn't need to be defined. So if I make a hollow circle and encode it like that with this membrane and with the hollow part that contains the 8 vertices, I should be able to put it right on a chess set. So I got a nice little magnetic chess set. I got some magnets, and if you look, this here is the 2 portions of the cone, one part of the Dixie cup, the unfolded Dixie cup. So what I did is I mapped that to a corner of an entire piece of paper, right? And then I'm able to contain it with a prime number here, with portions of 7 uniform circles, right? With 7 of them being uniform, sort of containing this circle within a square. This is a fractal of every piece on the chess set, right? So as long as I remember which fractal I'm at, that's why I've got these cubes here, so that I can contain an axis inside of a cube as well, right? This cube is directly transferable to this, my little mushroom cap here, this little baby, because the cone, or the cube, sits very nicely just inside here. Still leaving the hollow axis for the differentiation that I need. The other nice thing is I can encode it in a single shape, just like this. So this is the two states of my bell-shaped curve, literally. And then I've got a front and a back that is just like the pieces of paper here. So I can, using the vertices of my cube, which line up with the two lines that are on this pencil sharpener, which is sort of an odd thing to have two lines, right? That contain within it two circles, that contain within it an outer membrane. So the floating point problems all have to do with the center of the circle is not the axis of rotation, because this is transposing as it moves along the arc of a larger circle, just like spinning on an axis when you're in an orbit. So my idea with this is to be able to map this for the lines, turn it into a timeline with a repeating fractal that is contained here, right? Transfer that in a timeline and just sort of reduce all the variables into this cone. And then after doing that, the other nice thing that I'll be able to do is I'll be able to represent the three different phases that are symmetrical on the ping pong ball and just one variable phase here, and compare it to phase A, B, and C in an alternating current. And this is the difference between A and B, B and C, C and one completion. So I've got a fractal within a fractal, because this will be spinning, right? This will be spinning on two different axes. But as this moves around in an orbital sort of larger circle, all of this is fixed within the bell. So this is just sort of phase A. Phase B will be directly butted up behind it. Phase C will be directly ahead of it. And essentially, I'm containing the axial variables on two planes. One is the equatorial plane of a sphere, and one is the larger plane of which this is a tangent line. So we'll see how it goes. I'll let you know, but that's when you see me using all kinds of weird ratios and relationships and things, that's why. Thanks.